So, no, Richard Katz, one of the co-organisers of this program, and I'm very pleased to be speaking right here.
Thanks, John. Thanks for making this a great workshop. It's really been very interesting for me, and I hope that everyone has gotten a lot out of it. I want to just quickly mention the third workshop, which I'm organizing, which will be at the beginning of June, a beautiful time to be in Cambridge, guaranteed sun and springtime weather. And the full program ends on the 17th of June. So if you come to the third workshop, you can stay for a week after, collaborate, discuss, be fruitful, and so forth. You'll see that we've got mathematicians, rock mechanics, volcanology, seismology, and geodynamics. So we're going to be talking about the tectonic scale, both how to model it and then how to validate models or understand observations in terms of models. So I think it's going to be great, and I hope that you will consider coming with your students and postdocs. Okay, so I want to talk about one of the questions that I think is the most important facing the magma mantle dynamics. And that is, why is melt transport apparently so fast? John McLennan talked about it a lot at the beginning of the week, and it's been alluded to throughout the week. I'm not going to necessarily convince you of any answer, but try to highlight what I think are some of the observations from both the theoretical and the observational perspective that sharpen this question and make it quite a challenge. And I'm going to focus on mid-ocean ridges because, in some sense, that's the tectonic context that I think is simplest to model, but also because they're probably the second most prominent feature of the surface of the Earth, the most prominent being continents. But after continents, if you block out that, then the next most prominent thing is this seam that traverses the oceans and sometimes goes right up onto land. Not so easy to see, but right there in Iceland. So that seam is 80% of the volcanism, and it resurfaces 2/3 of the Earth's surface every 100 million years. So we're kind of paving the ocean floors with magma that's coming out of mid-ocean ridge volcanoes. And a simple cartoon for those who are not geoscientists. These are the plates of plate tectonics. Far-field stresses pull them apart at a mid-ocean ridge, and the passively driven mantle flow leads to upwelling and decompression, changing the solidus of a parcel of mantle and leading to melting, melt segregation, and eventually volcanism. And 75% of the heat flow comes out of mid-ocean ridges, and Peter Driscoll spent a lot of time talking about that. Just to emphasize that understanding mid-ocean ridges is a big part of understanding the overall heat and chemical budget of the planet. So here is a leading order, maybe, picture of a mid-ocean ridge. Plates spread, driving this corner flow, decompressing parcels of mantle eventually cross the anhydrous solidus and begin to melt, and with progressive decompression they melt more and more up to about 20-ish% before they reach the ridge itself, and some don't make it there. They get transported off to the wings of the melting regime, and potentially there's some mechanism that focuses melt towards the ridge axis. And a kind of leading order, carry on with this leading order picture, in places where the mantle is hotter, the solidus is deeper and the extensive melting are larger because, and this is a pressure temperature diagram, as the mantle ascends and crosses the solidus, it gets further above the solidus before it reaches the cold thermal boundary layer just below the surface of the Earth. In a colder ascending mantle, the solidus is reached at a shallower depth and the extensive melting are less. And these points represent averages of the chemistry of mid-ocean ridges, and that this chemistry has been normalized in a way that I don't really want to talk about. But effectively, this is kind of giving you some information about the chemistry of melts before they sit in a magma chamber and get modified by crystal fractionation. And sodium is an incompatible element, so when you melt more, you dilute the sodium in the melt, and when you melt less, it's richer. And so you can see that this global data set really is supporting this. Axial depth is the depth on the seafloor, so these are deep, and they have high sodium contents because the extent of melt is less and the mantle is colder. And when the mantle is hotter, you get more melting, you dilute the sodium, and you have a very high volcanic edifice. Okay, so that leading order picture is great, but when you go out and look at ophiolites, which supposedly represent, the mantle, the asthenosphere beneath what are either mid-ocean ridges or, in this case, potentially a back arc spreading center, but for our purposes, that's not an important distinction. You see very complicated geological evidence that melt transport is not uniform, that in fact it's localized into channels, and that those channels may dissolve away certain minerals and leave others. And the picture is not of a uniform triangle of porous flow, but rather of something where flow is localized and complicated. And the geological evidence has been summarized in this early paper on the subject. Sorry, no, this is not the summary of the geological evidence. What this is saying is that the melts that come out are far from equilibrium with periddotites or these gray materials, right? But they are in equilibrium with the dunites, which are these in the schematic diagram, these white materials. So it looks like the melt that's erupted, although it was produced by melting of this stuff, has been transported through a network of channels to reach the surface. And this may help to explain why we see these uranium series disequilibria that have been discussed at length, well, especially early in the week. So this is uranium and thorium, so that's the parent isotope over the daughter, although this is a stable version. This is the daughter. So this is a kind of normalized element ratio. And this is the isotope that's produced by decay versus one that's stable. And so what happens is uranium-238 becomes uranium-230, and that all happens along this black line unless the elements get fractionated from one another. So if you fractionate uranium and thorium, then you, by melting, then you enrich uranium and you move to the left. But then the decay of uranium leads to moving down on this axis until you come back to the equiline. So the fact that you see a lot of data above the equiline means that there hasn't been enough time for that decay to take place. And in this case, it's the decay of uranium to thorium with a half-life of 70-ish thousand years, right? So there are other isotope systems which give you other age constraints, but that's what's shown on this plot. And then, again, going back to something that was shown earlier in the week by John McLennan, this is the pulse of volcanism that's observed during deglaciation of Iceland, which is taking place pretty much contemporaneously. And so I don't know what the error bars are on the geological measurements. I know that there are error bars on them. But if you really want to have melt transport that takes melt from depth beneath Iceland up to the surface to supply this pulse of eruptions, then that tells you that you've got really quite fast melt transport speeds. These speeds certainly will explain the uranium series disequilibria, especially thorium, but will also potentially explain the more short-lived isotopes being in disequilibrium as well. But what I want to discuss is that this range is quite a challenge to understand theoretically, and I don't think we have an answer to that yet, but I think it's one of the major questions that the community is addressing. So I want to just summarize that introduction by saying maybe a mid-ocean ridge is some sort of background melting rate, which we've understood for a long time, plus some amount of channelized flow and reactive flow, or something else that leads to localized melt transport, and that's something that we're still struggling to understand. So this slide is to show you the mechanical model, which you've seen several times now. I'm not going to talk about it because I think other speakers have done a great job in explaining these equations and their physics. What I'll show you throughout the talk will be solutions to these equations, not in every case, or simpler versions, right? So we won't be adding physics to this, but we might be taking certain terms away. But I'm not going to put these equations up and discuss them again in this talk because this encapsulates all of the physics. Just to point out that C is the compaction rate here, and we've made a Boussinesq approximation. And also that if you do a little bit of scaling analysis on this, you come up with a characteristic speed, W naught, which depends on characteristic permeability. This is the characteristic buoyancy of the melt, and porosity and the viscosity of the melt. And if you put in background values that correspond to this triangular melting regime and diffuse porous flow, then you'd expect something like a meter per year. So we've got 2 to 3 orders of magnitude difference from that we would need to explain if this model is to be successful in explaining those rates of transport. So I'm going to start by talking about some reactive flow modeling that was developed by Einat Aharonov back in the mid-90s and carried on by Mark. And these are the chemical models, so this is just concentrations in the of some element in the solid and the liquid, porosities and densities, and this is the melting rate and the concentration difference from what's being created by melting. So as you put stuff into the liquid due to melting, this is what you're putting in. The concentration difference between those two things will drive melting. Some diffusion. This won't really matter because we'll just assume that the solid has enough stuff that it can always supply the what is undersaturated in the liquid. And if you do a little scaling analysis on this equation, what you can come up with is that the melting rate should go as the gradient in the equilibrium concentration of whatever it is that is being transferred from the solid to the liquid phase. So
velocity.
Yeah, that's right. I've left off the speed of the melt. Sorry about that. So the flux is melt rising up through a concentration gradient, and as it rises, it's undersaturated. And the rate at which it undersaturates is W times this concentration gradient. And then there's the difference between the equilibrium concentration and the melt that's being produced. So if this is very small, then the melting rate is very large. And if this is big, then a small amount of melt can satisfy the return to equilibrium, and the melting rate will be small. And I'll come back to this again. I want to make a quick point that the model of conservation of energy that was used in these papers is shown here. Not to criticize, but to point out that in these early models, the authors did the sensible thing, which was to do something simple first. But time has passed, and we can now ask what were the consequences of that choice. And I'll discuss that later. Okay. So here's what I was talking about before. Here's an equilibrium solubility curve. So this is a very simple model with a linear solubility curve with height in this case. And this is a sort of schematic of what the liquid would look like as it rises up. So it might have been in equilibrium at some depth, but as it segregates from the solid and moves upward, it goes out of equilibrium. Reaction is continuously bringing it back towards equilibrium, but it maintains this roughly constant distance from equilibrium in this calculation, which is something related to 1 over the reaction rate. So the faster the reaction rate, the closer these two curves are to each other. And then this is to represent crystals which are being melted, and there's some compaction, but the whole system is upwelling. So Einat did a stability analysis and took a very simple background state. It was not entirely rigorous, but quite effective, and came up with a very simple background state. These things are supposedly a function of z, but in fact she took them to be constant. And that allowed her to compute these nice patterns, these nice eigenfunctions, and this is the porosity eigenfunction, compaction, and you can see that there are high porosity and low porosity channel-like features. And Mark extended this and looked at diffusion, and so here you have a dispersion relationship for these channels. The growth rate is on the y-axis and the wave number is on the x-axis. The compaction length is right here, so we're seeing things smaller than the compaction length. Wave numbers that are larger can grow, limited by diffusion on this side and compaction, and by compaction on this side and diffusion on that side. So numerical solutions are also possible, so this just illustrates a bit. This is the porosity, and you see these channel features coming in and out. I'll play it again. This is something more or less like what you've seen earlier in the week with porosities getting up to 10-ish%. And this is what might be the geological prediction, is that you can exhaust the soluble phase. And so you might produce patterns of what would be Hartsbergite and Dunite, the blue being the place where there's no soluble phase left, and so you've got a geological record of this kind of flow. Mark Hess and colleagues did a more detailed analysis of this same system without the energy pretty recently, and they made this nice map of the behavior of the system, which was sort of mentioned in Aharonoff's work, but not really dwelled upon. And that is that you need a big solubility gradient to get channels, and you need a big fluid velocity. So when the fluid velocity is big, you're down here. So you need fast segregation, you need strong reaction to get these channels. But if you do assume those kinds of things, then you might, from these early models, expect velocities of up to 100 meters per year, and that's really encouraging because that is getting towards what these geological and geochemical constraints might require. So reactive flow and compaction can produce channels if melt segregation is fast and if the solubility gradient is large. But these models are probably too simple because they neglect conservation of energy and latent heat. And in the end, we are talking about melting, and that's a thermodynamic process. And thermodynamics is complicated, and it may not be simple to put everything you want into a model like this. But you ought to at least try to conserve energy. So let's do that. So let's talk about an energy model. This is a temperature equation, and here it is in terms of enthalpy. Of course, these go back to Dan McKenzie, 1984. But what I'm going to talk about is a formulation and coupling with a phase diagram, which is coming from some work that I've done and from Ian Hewitt's work. Ian is back here. Yeah, Ian's here. So you can think about this in terms of temperature or enthalpy, where H is a bulk enthalpy. And in both cases, you've got transport of sensible heat, transport of latent heat, diffusion, thermal diffusion, and work against gravity. And then you need some sort of petrological model to close the system of equations. And what we've used in these papers is a very, very simple linearized phase diagram where there's a solidus temperature represented by the green mesh and a liquidus temperature represented by the black mesh. And they're located in a space of two components, two thermochemical components with pressure and temperature. And so this is the Clapeyron slope here, and this is a compositional slope. Now, the mantle is much more complicated, as we've talked about this week. So a two-component system is grossly inadequate, but it's an incremental step in the right direction, and maybe someday we'll be using full-blown thermodynamic models of 13 components, but I don't think it'll be soon. Here's a numerical solution with energy and conservation showing you this leading order behavior, right? Homogeneous mantle, which is coming in through the bottom of the box, begins melting at some solidus depth, ascends buoyantly through the pore space and is focused towards the ridge axis by the compaction pressure gradients which appear along this impermeable boundary where freezing takes place. These are isotherms, so this is the mechanical lithosphere and the plate moving out, and these white dots are incompatible trace elements. Let's say they move with the melt where it's present, and where the melt is not present, they move with the solid. So they're showing you something about how material moves through this system. And we've done all this in the context of this linearized phase diagram.
Rich?
Yeah.
What's going on at the axis in this simulation?
Yeah, I mean, that's is an important point. What is happening here is that instead of allowing melt to just pool because there's a cold thermal boundary layer above where it would freeze, we've created an internal boundary condition, and gravity drives the melt into this internal boundary, and we account for it and take it out of the domain. So it's like a very localized negative source term, right, that we put right here that just allows melt to go out of the domain.
Yeah, so is this from reactive, or you assume you're actually in chemical equilibrium? That it freezes solid when it's cold. It's below the solid. It's porosity 0 at the solid.
Yeah, I mean, I guess you could say this is a reactive system in the limit of very, very fast reactions. So I wouldn't draw
It's an equilibrium system.
It's equilibrium. I wouldn't say that an equilibrium system is not reactive in some sense. It is reactive. It's just the reactions are in equilibrium, and so they're taking place in a...
Before you go any further, right close to the axis, your channel of high porosity looks as if it disappears. What have you done there? It goes red. Do you see it goes...
The reason that this higher porosity becomes lower porosity right here is just that there's an acceleration as this boundary slopes upward. So melt is moving faster and at a lower porosity. I think that's not an unexpected feature, but you might disagree.
The sink at the axis, that's a function of the plate divergence rate, or is that a function of the ascent of melt into that?
The latter. It's not imposed. It's simply a cut within the domain where melt that crosses that cut is removed.
Is it removed at a specified rate, or
No.
or it's an open boundary?
It's an open boundary condition, right? So the spin up leads to oscillations in crustal thickness, but it comes to a steady state where you see this stable pattern and melt just goes out.
So the spreading rate of the plate doesn't induce like a viscous head or something to draw out the melt?
That is something that you wouldn't... well, of course, there is corner flow here, and so there is a low pressure, and that appears within the domain. But we don't add an extra suction because we simply wouldn't know how to calculate it. I mean, there are a lot of challenges associated, especially when you have a heterogeneous mantle and so forth, with getting this to be sort of pathological, and sometimes hacks are needed. But in general, what we do is we just try to allow a kind of as free flow as is possible there, and it doesn't always work perfectly, but
And nothing melts below 50 kiloliters or thereabouts.
not in this model. Yeah. So, of course, it depends entirely on the parameters you choose for this phase diagram. But I'll show you more sophisticated calculations later. So now we want to come back to the idea of reactive flow, and this was Ian's idea in 2010, but of course it goes back to Neil Reeby's work in the 80s. You try to put these equations into a form that can be solved. So this involves the zero compaction length approximation, which we've probably discussed. And then you can compute for a vertical column temperature, degree of melting. These are the compositions in this two-component space, and the porosity, which you'll see grows, and then relatively uniform gradient. And then the details of these boundary layers aren't important, but there's some melt segregation in this vertical column. And then we like to perturb this one-dimensional solution in 2D with channel-like solutions and see if it grows. And now this is like what Aharonov did, but with a more reasonable background state, with a more reasonable base state, and also with conservation of energy and so forth. Not that it's a simple difference from what she did. There are a number of differences, but still, it's quite close. So Ian says the approximate stability condition has a simple interpretation. The driving mechanism for instability is that the melting rate increases with increasing flux, so we saw that already. And this is countered by compaction, which also increases when the melt fraction increases, and therefore tends to stabilize small perturbations. And furthermore, that only if the melting rate dependence is strong enough, which requires that the background flux Q is large enough, so this is the amount of melt that's going through the system, can the system be unstable. So here we see the melting rate that came out of these energy conservative models. V bar is the weighted velocity of the melt in the solid. So in here we have phi W, and of course that is our melt flux, right? And that drives melting. So this is the decompression change of the solidus. This is the loss of heat to adiabatic decompression. This is a penalty due to the phase diagram. So as you melt the solid, it becomes harder to melt because you're taking away the easily meltable stuff. And here's the latent heat penalty. This is about 10 times bigger than this, at least for the simple model that we're considering. So really, it's the latent heat penalty that you're paying, and that is limiting the amount of melting that can take place in a channel. If you melt too fast, the temperature goes down, you reduce the melting rate. So this is an important part of this channelized flow question. To channelize flow, you have to overcome the cost of the energetic cost of melting, and that was left out of early models. What Ian pointed out was that if you flux the bottom of the domain with a sufficient supply of melt, then effectively you can overcome that problem and you can produce channels. And another way to think about that is that you've just started your domain not at the bottom of the melting column, but somewhere in the middle, and that you're going to just allow as much melt to flow in the bottom as the dynamics would like to handle. But there's another way you can look at this, and that is, suppose you do have the full melting column, but now instead of taking a latent heat, which you think is reasonable, you just take something smaller. Well, Sam Weatherly showed that that can also lead to channelization. But something to notice here is that these channels are at the grid scale, unlike what was found in the earlier stability analysis of Aharonov and so forth. So that's a bit of a problem. What about chemical heterogeneity? Because one source of additional melt that could be fluxing the system from below is the fact that there are parts of the mantle which melt at lower temperature. They're recycled basalts or primitive materials that have never been melted before. So here's a simple idea developed initially by Norm Sleep, and John and I came back to this in 2011 and worked it out in a bit more detail. Suppose you've got some blob of material. It could be a filament, it could be a sphere. The difference between those two really is just in the details. It melts at a lower temperature, and therefore as it rises up it begins to melt, and it's putting sensible heat into latent heat, which is keeping its temperature lower than the surroundings. So now you've got a temperature gradient, and heat is diffusing into this blob, right? Which makes it melt even more. And so melting is enhanced. You get a cold halo around this in the ambient mantle where melting is suppressed. And when this pod of melt makes a connection with the ambient melting regime, which would have been there in the absence of this heterogeneity, then there is a large flux of melt, and that can lead to channelization, as we see in this movie. So here's the blob moving upward, cold halo around it. When it connects, you see this flux of melt and channels form. So there's another possible way to do things, and here is the melting rate that Sam worked out for this heterogeneous model. So here again in this prefactor you see the latent heat penalty and the phase diagram penalty, and here in this term A you've again got the Clapeyron slope, and the decompression, and this is the part that Ian had. But we now also have heat diffusing into the colder areas, and we have the chemical diffusion as well. So these two things can also contribute to the melting within a channel, just as they contribute to the melting within a blob of heterogeneity in the mantle. Right?
Your flux, I feel like I rag on people about Galilean invariance, but your v bar dot k,
Yeah.
it's not a relative velocity. I mean, if it's all, your melting flux could depend on frame of reference, or am I misreading that? Is it relative to, in other words, if I change my frame of reference to,
I think, your frame of reference is a gravitational field, so the gravitational potential has to be the frame of reference. So it's moving with respect to this gravitational potential, and that's why it's melting. I guess I would like to discuss that with you offline.
Pressure.
Yeah.
Yeah,
Yeah. So we decided to have a little bit of fun and just to create stochastic mantle heterogeneity, put these into a mid-ocean ridge model and see what comes out. I don't really want to dwell on this. It's cute. Random blobs and a sort of smooth noise. Here we are kind of imagining that the mantle heterogeneity is filaments that are below the resolution of the model, and so we're going to just say there are more filaments in places that are red, more filaments in places that are blue and less filaments in places that are red. And this is expressed in terms of a perturbation to the melting temperature. So blue melts 50 degrees cooler, red melts 50 degrees hotter, and that's why we call this refractory and fertile. And we filtered, so this is wavelengths, we filtered out the short wavelengths so that we can resolve this on the grid scale. Of course, mantle heterogeneity goes down to the grain scale.
blobs plus noise in the.
No, it's just two scenarios. And in fact, I'm only going to show you results from this one. It's not actually very different what you get. So here's just a movie. This is the porosity in a log scale, so 1%, 10%. And this is the perturbation of the solidus. So this is refractory and fertile. These are fertile blobs. You can see it. So. And not surprisingly, when you have this heterogeneity, there are preferential pathways which are more fertile, and those are the pathways that melt takes. But you also see some channels forming vertically, which transport melt more rapidly, and then kind of Plinko transport of tracers that can move through the system. So here's a way to get channelized and rapid melt transport in the mantle heterogeneity. I mean, we kind of know that the mantle is heterogeneous. So you could say, well, of course, you make a complicated model, you get a complicated result, but the mantle is complicated. There is heterogeneity there. What we don't know is what is its length scale and what is its amplitude. So, of course, if mantle heterogeneity was at a length scale which was basically, much bigger than this box, then it wouldn't help you with this. Yeah.
So what would happen if you have like potential temperature heterogeneities or temperature heterogeneities? Would it stabilize against channels, or what would you expect?
Temperature heterogeneities. So you create temperature heterogeneities through this melting process. But if they come in the bottom of the box, I mean, it depends a lot on their length scale. And I would argue that because this mantle has not been processed through a melting region or near the surface for quite a while, the length scales are going to be very long because of the thermal diffusion.
But
so
you would basically, the place that would be the most amenable to melt will diffuse the excess enthalpy away, right? It's kind of the opposite problem. It should.
Yeah, I mean, you would smooth out those variations, and you'd probably smooth them out before you get them into the melting region. I think it behaves pretty much as you would expect. I don't think that there's anything tricky there. I just, a mantle plume, right, could potentially come up near the ridge axis, and then you have Iceland. So I don't know if I answered your question, but maybe it's because I didn't really totally understand it.
Do you need some sort of minimum level of heterogeneity? I mean, since Morbs, when you look at isotope plots, they tend to be more, narrower, and these distributions, like in helium, for example, is very narrow.
Yeah.
Which is not very heterogeneous. Do you need? I mean, is there a minimum amount of heterogeneity you can do to get these channels, or do you need something as heterogeneous as
Yeah, there's
OIB source, right? Which would be really all over the board?
I mean, first of all, the answer to that question depends on the sort of petrological parameterization that you use. So I wouldn't argue that I can give you an absolute answer. But in the context of the models, yes, we had a sort of little behavior phase diagram, and I stupidly didn't put it into my slides. But if you ask me afterwards, you need a sufficiently large amplitude of heterogeneity for it to do this channelization trick. Yeah, Boris?
The spacing of your channels, is this controlled by the spacing of your heterogeneities?
Yeah, in these calculations it is. I mean, as you saw with the one that I showed you, the column model, that blob produced channels that were not spaced according to the locations of different heterogeneities, but of the size of the channel. One of the things that I'll conclude at the end is that we need more analysis. I think we need to come back to the stability analysis and extend what Ian has done with more sophisticated treatment. But I'm not sure that I'm going to be up for that sort of thing. But I think there are people in the audience who maybe are, and I would say that this is an important problem to try to come back to and analyze, and especially because you see the channel width going down to a grid scale. So, you know, is that because there's missing physics, or is it just because we haven't done a good job of resolving? You see what I'm getting at. I just want to say here, these are travel times from the point at which something becomes partially molten until it reaches the ridge axis for only parcels of melt that reach the ridge axis. For homogeneous random blobs and smooth noise, I don't really want to worry about the difference between these two. But what you see as a function of the path length, so what you see is that sometimes, generally short path lengths have short travel times, but sometimes intermediate and longer path lengths can have short travel times, and that's just because of channelization. Of course, these travel times, you know, are going down to around 25,000 years. So if you want to satisfy lead-210 or radium, that might not be good enough. But on the other hand, I'll come back to this at the end, the interpretation of uranium series is difficult, and we need to think carefully about what it means. So I want to move on to the last part of the talk, or sort of the second to last, which is the role of volatiles, because of course major elements are very important, but volatiles are also a key control on mantle melting and on the behavior of melt transport. And this is, you know, Toby has done an amazing job with this project, and so a lot of everything that you see is a result of the work he's done. So what we've done is to make the phase diagram a bit more sophisticated. So now we're in a ternary system, and this can, you know, his methods will scale up to 6 or more components. But we assume solid solution between all the components. So this is like a dunite component. This is a morb component, not after it's been erupted, but when it's as part of the mantle. This is a little bit like what Ali has done in terms of analysis of the petrology of Iceland. We assume that there's some recycled component, and then there's some very refractory component. And then this is representing carbonated morb. So instead of just dealing with carbon as an end member, which has extreme behavior, we do something a bit more moderate. And what you can see is the solidus steps down from dunite to morb, and it steps down again as you go to this carbon-rich morb. And then, you know, this phase diagram allows you to calculate the solidus and liquidus anywhere in this 3-component space. And so for 100 ppm of water, this is what you get. There's the carbonated solidus as a function of depth, the hydrated solidus, and the dry solidus, and I actually can't remember what that line is. But here's a typical adiabat. So you see that you cross the carbonated solidus at about 5 GPa. Now these are data from Raj Dasgupta. If you allowed your solidus curve to follow this, then you'd be, you know, crossing the solidus at such great depths that your model would basically need to be a global mantle convection model. We don't want to do that. Plus, there's some question about the oxidation state, which controls where you actually would cross the solidus. But in any case, the general systematics are volatiles will lower the solidus temperature or increase the pressure at which you cross the solidus. And so we put this into the framework of a reactive disequilibrium and multi-component model. So reactive disequilibrium multi-component with an underscore, and for fun we like to call it Run DMC. So the Run DMC model is underlying the calculations that I'm showing you next. So this is the role of volatiles, and in particular here this is water. So mantle upwells, begins to melt at the hydrated solidus, and then as you approach the depths where you transition from water-rich melting to silicate melting, there's a very, very strong channelization for the same basic reasons that we saw in the previous calculations. There's a corrosive reaction going on that is leading to enhanced melting where the flux is greater. And so you get this strong channelization, and then it kind of fades out. And the reason that it fades out is simply because we haven't attempted to include the solubility gradient of silicate basically in this part. So this part of the domain is not reactive. This is the reactive part where the volatiles drive enhanced melting. This is weight percent going from about 1% in the dark colors to 0, and so you can see that porosities or melt fractions are higher in these channels. And then this is the water content in weight ppm, so you see that we've injected about 100 weight ppm, not very much, into the bottom of the domain. And with the melting it gets diluted, and these channels have larger melt content, and that's what makes them corrosive and drives melting there. So we think that this is potentially contributing to channelization, not that there's not important reaction going on in this part of the regime, but that channelization may start even deeper, particularly down here where you have garnet and the different partition coefficients, and this may help to explain uranium series because you may transport melt from deeper at greater speeds. Okay, so let's just plunk this into a mid-ocean ridge model and see what happens. I mean, I make that sound very simple. This was a good year of Toby's life. Here we have a picture with water and carbon dioxide, the carbonated solidus, the hydrated solidus, and the volatile free solidus. This is the log of porosity, and you can see massive variations. There's some pooled melt here, channels. These are, the red lines are streamlines of the melt. Some melt gets to the ridge axis, some melt doesn't. This is the log of the liquid flux, so phi w, little w, in meters per year. You really see the channelization here. You can see channels forming at the bottom of the silicate melting regime and penetrating upwards. And what else did I want to point out about this? Right, that this is going up to something like 1 meter per year in the flux, and at a porosity of 1%, that translates to about 100 meters per year of the transport speeds. So again, we're seeing rapid transport speeds here with channelization. And
what's your maximum porosity near the ridge? Do you have a porosity scale?
These things probably go up to a few percent near the ridge. So we've got a slightly different boundary condition here. It's a few grid cells over which melt is allowed to leave through the top of the domain because it is prevented from freezing. So in this disequilibrium formulation, we can just say turn the freezing rate off.
Roughly the maximum degree of melting on the axis.
I think, gosh, I don't know. Toby, is it?
I didn't understand the question.
What is the maximum degree of melting? So the extent to which a parcel of solid has melted when it's gone from here to here. I mean, by this point, it's only 1%-ish.
It will be of the order of about 15%, I think.
15%, yeah. So as usual, you know, with this fictitious phase diagram, one is loath to pin too much significance on any one number, but we try to come within observational constraints, though we don't try extremely hard. So, you know, if you wanted it to be 20%,
oh no,
you know, it could be 20%, but it would just be a trade-off in some other parameter.
I'm just trying to get some rough rules of thumb.
Yeah, yeah. I mean, one interesting thing is that if you change the potential temperature by 25 degrees with these models, you don't get 1 kilometer crustal thickness change, you get 2 kilometers crustal thickness change. And you say, well, that's about double what Paul Asimov thinks it should be. Well, I would argue, I don't know, maybe Paul doesn't know the number that well. But it's something that we could tune again, but I would say we're actually already doing pretty well. So, Paul isn't jumping out of his seat, so I think we're doing okay.
Do you want to address the fantastic heterogeneities that you're embedding in the upper mantle off axis?
I don't want to say too much about this because Toby is. I mean, I think you just have. Toby's going to talk about this at the third workshop, and there's a huge, interesting behavioral space and lots of interesting things that one can say. I want to stay focused on the topic at hand and let him
answer the hard questions.
Answer the hard. Yeah, exactly. I'll just sweep the details under the rug. He'll lift the rug and sweep them back out. So here we have the role of volatiles. Again, this is just for no volatile content, 50 ppm, 100 ppm, and 200 ppm of both carbon and water. And you just see, I mean, if there was any doubt that the reason that channelization takes place in these models is because of the volatile elements, and there's all kinds of funky plumbing. Yeah, all kinds of funky plumbing systems here. Okay, so let me not finish, but summarize. Early reactive flow models demonstrated the tendency of the system toward channelization if it's sufficiently corrosive, but they neglected the energetics. When we incorporate the energy conservation, we note that channelization can be suppressed, but if you bring back in certain things like mantle heterogeneity and volatile elements, you can get that channelization back. So I think the question then becomes, how does this compare with geological observations, geochemical observations? Is there evidence for or against these kinds of things? And I don't think we have great answers to. I don't have great answers to those questions. And the phase diagrams are designed to capture some aspect of the behavior that we're interested in, but we run the models and then we find, well, there's maybe another aspect of the behavior that they weren't designed to capture, which we've excluded. So, one way to handle this is to just keep tweaking the phase diagrams to try to capture more of the physics, but eventually you might as well just put a sophisticated thermodynamic minimization process in there, and some people are already doing that. Joe and Bernard also is working on incorporating chemical potentials and more sort of sophisticated treatment of the thermodynamics, chemical thermodynamics, into these models, and I think that that's a very promising direction. But then you come back to the observations, and some people will argue that 100 meters per year just isn't enough. You can't get some of the radiogenic elements, and you can't potentially match these observations from Iceland if you don't have 1,000 meters per year. I think that these observational systems are complicated. The geology of Iceland is complicated. Uranium series is complicated. Not to say that we understand everything about melt transport in the mantle, but we do understand something about the physics of this compacting system. And I would say even if you can open up somehow cracks or open pipes in the mantle, you still have to face the fact that if you have a high permeability pathway. Suppose this is the Earth, this is the mantle. Here we have porosity greater than 0, and we want to take this melt up to here, where we are. Right? So we just drill a hole all the way down, okay? But this is a ductile material, and we've connected a, extremely low pressure to extremely high pressure, right? And so on the one hand, melt would like to flow out. On the other hand, this is low pressure now in here, and this is high pressure, and you just close the hole, right? This is the whole point of these channelization calculations, is that compaction will close the channel. And so you have to melt fast enough to keep the channel open. And there has to be a balance between these two things. Dan is shaking his head. He may have like to comment, but no matter what you do, you have to face that closure versus opening challenge, I would argue. So these things to me are hard to understand, and I would like to say that the geological observations have uncertainties too, and the interpretation of uranium series is extremely difficult, and that's a problem which we ought to come back to. I think it was intensely pursued by Mark in the earlier days. We ought to come back and think
Pleistocene, yeah.
about that. Again, yeah. Lastly, I want to say one more thing about pressure variations and how they might come into play on this system. So Iceland has massive pressure variations. When you deglaciate and you remove, kilometers of ice, you get a very, very strong depressurization. But sea level may also be playing a role. And if you take the ratio of the density of seawater to mantle, it's about a third. And if you take the rate of sea level change versus the rate of mantle upwelling, again, a factor of a third. And so sea level can perturb the melting rate, the decompression melting rate, by about 10%. Okay? So it's not big, but it's also not negligible. So what we've done is we've taken these models and we've put imposed pressure variations on the top, and in the form of this sea level reconstruction. And so these are curves where for each spreading rate we've taken different background permeability levels, so more intermediate and less permeable. And the frequency content of these curves, that is the transfer between the frequency content of sea level and the frequency content of the crustal. This is crustal thickness, or deviation from the mean crustal thickness. The frequency content depends on the permeability. High frequencies will emit more. High permeabilities will emit more of the high frequency, and you can look at the spectral analysis of this sort of thing. So this is the spectrum of the sea level. You can see the Milankovitch peaks at the Milankovitch frequencies of 140 in about 20,000 years, and the extent to which each of those concentrations and power is transmitted into this depends on the permeability that you choose, and we've analyzed this in some detail. And these are admittance curves, so this is frequency and the ratio of crustal thickness variations to sea level variations in that frequency band. And so you see the system is sensitive at some intermediate frequency. And the reason is basically that if the period of sea level variation is about equal to the period, to the time it takes for melt to be transported out of the system, then you can have non-cancellation. So this is enhanced melting with depth. This is diminished melting due to earlier sea level change. If you integrate this pink curve, you get a large signal. If you integrate this dashed curve, you're integrating of sea level drop, sea level rise, sea level rise, sea level drop. So going back in time, this is for very slow melt transport, or fast variations in sea level. This is for slow variations in sea level. Their rate of change of pressure is small, so you don't produce a lot of melt. So there's this kind of sweet spot in the middle, and that potentially gives you some constraint on the melt transport if you believe this slightly far-fetched idea that there are variations in melt supply. So I didn't include this because I think it would take me way over time, but we looked at spectra of crustal. We don't have spectra of crustal thickness. We have spectra of seafloor bathymetry across the axis, and we see peaks in these at the Milankovitch frequencies. And there's a vigorous debate going on about whether those represent tectonic features, faults, and overtones of those faults, or whether they represent variations in melt supply. And of course, we argue that the answer is somewhere in between. I don't want to dwell on it anymore because it's certainly very controversial, but I think it's intriguing. The point being that if it is true, it doesn't. It argues that there's some amount of melt transport which isn't at this, kilometer per year superhighway to the volcano. So porous flow models may never give transport rates of a kilometer per year. And so if some of these observations are correct, then exotic mechanisms are needed, maybe emergent fractures or fractures in quotes because they may emerge from the grain scale are needed. And certainly I wouldn't discourage anyone from thinking about that. It does seem like it's plausible, but of course, as I said, I think you need to overcome the fact that these are going to be very low pressure and they're going to want to close. So they have to be held open by melting or some other process. interpreting U series is not straightforward, and we can talk about this, but Mark's done some interesting work on that. And the thermochemistry is a crucial part of the models, and it's something that we ought to expect people to incorporate and analyze in the future, because that's, I think, where a lot of the answers to these questions will lie. So that's all I have to say. Thanks.
Thank you very much, Rich. Questions? Dan, do you want to kick off?
I want to pick up on this business. What you're assuming is that is a permeability porosity relationship. Now, everybody knows that depends on porosity, but it also depends on the length scale A, right? And all you have to do for this business, right, is to simply say that you want to increase your compaction length by essentially producing channels on a scale which is large compared with the grain size. And all you've got to do is to say that the channelization takes you from a grain size to channels of spacing of about a meter, and then you're done. And all the uranium series and the stuff from the deglaciation is then fine. The channels, just like they do on the grain scale, open and close. But all you have to do is to localize things on a rather larger length scale than the grains, and then you're home. I don't understand why people are resisting that, because I mean the whole what we're seeing is the channels actually joining together. Everybody who does these calculations gets that, but they're not working on the scale of the grains, and the course your grid size is enormous compared to the meter.
Of course, yeah.
And then you're out of all these troubles. I mean, and it seems to me that's just the simplest solution. I know
it's so simple that somehow we haven't been able to work it out, but we should explore these ideas. Yeah. No, it's not just as easy as cranking K up. You have a budget of material and energy.
Arbitrary to make your permeability that much bigger by imposing these larger pathways? I mean, how do you get there?
Well, I mean, you've seen how you get there. The process on the process of compaction collects stuff into channels. What you're trying to do is to say the permeability in those channels is governed by the grain size, right? So it's a millimeter rather than a meter. And if it's a meter, you're out of trouble. But what you can't, but the channelization, if your grain size in the channels is simply a millimeter, it doesn't help you. You still then got to have special arguments for the uranium series, special arguments for the decompression. But all you've got to do is to say, no, your grain size is not actually what governs the spacing of the melt channels in these porous regions. And then you're out of trouble.
Yeah, I mean, the permeability of the system is a property of the grain size.
No. It's a property of the spacing between the channels which the melt...
Okay, I mean, if you coarse grain to a certain level, then the effective permeability is
no, not coarse graining. I'm saying what happens at the physics at that level, right?
Okay.
If the thing channels at that level, then that's what you should put in as A.
So coming at this from a different perspective, I mean, to keep a channel open, you have to supply it with enough...
You don't have to keep it open. It's exactly like exactly the same equations, but just with a different relationship for the permeability and porosity.
Okay.
That's all you have to do.
Okay.
Sorry, Mark. No, sorry, I just want to follow up on that.
Actually, let's take N divide, because following up on that might lead to just an endless discussion of that, and maybe we should come back to it in the break.
You know what I'm going to say. Well, hold on. Yeah, go ahead.
Yeah, Anne had her hand up from the beginning, so let's have Anne.
No, I just had a naive question. We talked about volatiles, but
Yeah.
at some point, can they exsolve, and could it help to speed up the channeling upwards?
Exsolve into a gas phase.
Mm-hmm.
I think that they would have to exceed the solubility at a given depth, and I guess that where they're highly concentrated at depth, the solubility, I mean, it's probably some sort of supercritical phase. As you go shallow, yeah, I would say so, but I don't know if you could get there in the mantle.
But for example, in the case of Iceland, so when you unload the ice, it's going to affect mainly the shallow portion. So I was wondering if, in this case, you could exhaust the volatiles and then help to the channeling and going up.
Yeah, yeah, down to a certain depth, I think that could potentially create a kind of a shift in the mode of melt transport where you're not explaining it by the same mechanism. This massive unloading leads to a different mode, and you wouldn't expect it to obey the same kinds of scalings. So yeah, I definitely think that's a good point.
How does including the shear controlled strain localization will change the picture?
It is included.
It is included.
I mean, you know, I think that, I mean, this is somewhere where I guess Stan wouldn't disagree so vociferously, but you know, when you when you have of course, you know, the people do these experiments and they're very fast and they're very small, and the ratio of the compaction stresses to gravity is very large, and they produce beautiful bands. And I think near a permeability barrier, as you might find, you know, just beneath the crust, then it's not that gravity is less, but you're in a confined system. In the open mantle, gravity is much stronger than compaction stresses. The strain rates are small, the stresses are small, and gravity is strong. And you know, localization according to that mechanism is, I don't think, an important factor in the calculations that I've done. It's certainly worth looking into, and I'm collaborating with Matt Nepley, and he may mention this, to try to revisit those calculations and see whether there are conditions in the mantle away from barriers where those kinds of localization effects could crop up. Dave. Oh, sorry. I'm not in charge.
Mark has been waiting.
Yeah, I mean,
Well, other Mark. Mark has.
Yeah. I mean, how sure are we about the, you know, that calculation that tells you how deep below Iceland you're melting? Presumably is that based on some simple elastic model? If you had some sort of viscoelasticity, could that, you know, cause less of a pressure drop? Or I don't know.
Yeah, I don't want to speak. I mean, some of the authors, well, are in the audience.
Yeah.
Dan is. You know, I think that what they've done is a viscoelastic medium, but you could say it's an elastic layer on top of a viscous medium. And I don't think, as long as there's some elasticity in the problem, I don't think you're going to change the fact that it will depend on depth, and there'll be some kind of maximum at intermediate depth, and then it'll trail off. But I don't know. Maybe it's worth revisiting.
The depth is simply controlled by the size of the ice cap.
Yeah.
Not by anything else. It doesn't make any difference whether it's viscous or whether it's elastic. Right? The equations are essentially, I mean, if it's incompressible, the equations are identical, so that the thing goes to the same depth. So I don't think that's an issue, right? I mean, I think we know where the pressure release occurs. Right? What the physics then is another matter, but I think we know where the pressure comes from.
Go on, Mark.
Yeah, okay.
Just a comment, really. I mean, I'm actually reasonably agnostic as to what the permeability in the mantle is. It does depend on the scale which the melt organizes, but there is something I think we sort of lost. I should have said at the beginning, is if you believe that melting is beneath ridges is primarily decompression melting, okay, and then the flux of melt production is still bounded by the solid flow rates. It's the rate you make it. So if you want it to come out, if you make it at a fixed rate, and you want it to come out fast, then there can't be any melt left. I'm not saying there isn't. I mean, that may be the case, but that's just conservation of mass in quasi-steady state. So those are the kind of other bounds on these things that we need to think about. So if you really want, I mean, the 1D column says, it's simple, it says if you want the melt to move 100 times faster than the solid upwelling, then the porosity has to be 100 times smaller than the degree of melting. That's just conservation of mass rules of thumb. So, you know, these are the trade-offs If you make it more permeable, you have less, obviously you have less melt there. So if there's bounds on the amount of melt and the amount of melting, then we can maybe get at some of these.
Yeah, I mean, I think you have to think about it in that context of not just the mechanics of one isolated patch, but of the budgets of energy and mass. I would say that, I mean, this melting rate includes not just the solid, but also
Oh, no.
the
So that's an
liquid.
interesting question, the channelized one. So you can say, look, there's a background melting rate of just decompression if it didn't separate.
Yeah.
How much more melt do you get by the reactive flow? The number to untangle some of these.
But I mean, from the uranium, the other thing the uranium series does for you is tell you what it puts a upper bound on the melt fraction which can be present. And the astonishing thing about the disequilibrium is how small that has to be.
Yeah.
And I'm entirely happy that it should be undistinguishable from zero, because then you're not in the same problems with protactinium-231, which otherwise you're in real trouble.
And the rules of thumb there are if you want to separate them and you believe it's chemical, the porosity has to be comparable to the partition coefficient of the element. And that's so small. That's where that number comes from.
That's where that number comes from. Yes. And the problem is that I mean, to a chemist, uranium is a totally incompatible element. Well, it isn't.
I think we should probably continue these discussions
coffee.
over tea. Yeah. We thank Rich once again, and we'll come back at 11:25.
Thanks.